learned last time. So what we were looking at was model of random noise in resistors. Okay. So essentially a resistor which is supposed to give you a voltage proportional to current or current proportional to voltage has an additional current, or you can think of it as additional voltage, and that voltage is random, right? And that is the noise of a resistor. So if you apply voltage V, you have flowing in it V by R plus some noise current. Okay. And this noise current is such that it has zero mean. Okay, so if you do have a DC of V, the average current that flows is V by R. And the noise current at any two different times are uncorrelated. Okay. So this implies that it has a uniform or white spectral density. And the level of spectral density of the current is 4 kT divided by R, where K is the Boltzmann's constant and T is the absolute temperature. Okay? And equivalently the same thing can be represented as, so if I is V by R plus IN, if you force a current into a resistor, you get I times R plus some voltage. Okay? And this entire thing is represented as a noise voltage. And it's simply proportional to IN, so it shares all the properties that we listed here for IN. So Vn also has a zero mean, and values of Vn for any two different times is uncorrelated or uncorrelated. Okay. And the spectral density is again white, because Vn is related to In by the proportionality constant R. The spectral densities are related by a proportionality constant of R square. Okay. And it also has a white spectrum. Okay. So this is what we were looking at last time. And also this spectral density, what does it mean? This is SI as a function of frequency, and this is SP as a function of frequency. So if it is filtered by a filter of certain bandwidth, then the RMS value, the mean square value of the resulting quantity is the spectral density. In this case it's uniform, so the integration is just a product, the spectral density times the bandwidth. In general, it's the integral of the spectral density over the desired range of frequencies. Okay. So similarly, if you have the resistor noise voltage going through some particular filter of a given bandwidth, in this case we assume an ideal brick wall filter, its RMS value is 4 kTr times the bandwidth of the brick wall filter. Okay. So this is how we calculate the amount of noise. If we have a number of resistors in the circuit, we do this for every one of them. Okay, we calculate the transfer functions from each resistor to whatever the quantity of interest to us is. It could be a voltage, it could be a current. Then we calculate the mean square noise in that particular quantity. Okay. Now the units of SI, that is the spectral density of the noise current, are ampere square per hertz. So when you plot 4 kT by R, so the y-axis is in ampere square per hertz. But it's also quite common to plot the square root of this quantity. Okay, so it's exactly the same plot except that on the y-axis you plot the square root of SI. I mean, you still call it SI frequently, so don't get confused by the notation. Only you change the units to ampere per square root hertz. So in that case, this level will be square root of 4 kT divided by R. So similarly for the voltage, the units of spectral density of voltage is volt square per hertz. Okay, and again it's quite common to see square root of this plotted, volts per square root of hertz. Okay. Now, of course, you can go and calculate this for every case, but it's good to remember that kT is 4 times 10 to the minus 21 at room temperature. Okay, so it's a useful thing to remember. And the noise of a 1 kilo ohm resistor is 16 times 10 to the minus 18 volt square per hertz. It's usually more convenient to remember it as 4 nanovolts per square root of hertz. I just took the square root of this. Okay. So the noise of a 1 kilo ohm resistor is 4 nanovolt per root hertz. So if you remember this, you can generally scale it up for any other. If you have a 16 kilo ohm resistor, it will be 16 nanovolts per square root hertz and so on. Okay. So also it means that if you have if you pass the noise of a 1 kilo ohm resistor through a brick wall filter of 1 megahertz bandwidth, what is the noise? What is the RMS value of noise? Into 10 to the 3, right? Square root of the bandwidth. So it is 4 microvolts. That also gives you an idea of roughly the order of magnitude of noise we see in different circuits. So you can see that if you had a 1 mega ohm resistor, you would have a much higher level of noise voltage. Okay. Is all this clear? This is all just like different notations and so on. Nothing special. Okay. So did you guys calculate the noise of this circuit? What is the integrated noise of this circuit? kT by C. So output noise voltage square RMS is kT by C. What is the spectral density? For kTr by yeah. Everyone got this? So if you integrate this over the entire range of frequencies, we get, basically we can change this to okay. We get 4 kTr divided by 2 pi CR okay, and this over the limit 0 to infinity gives pi by 2, right. So we get kT divided by C to be the integrated noise. So the integrated noise turns out to be independent of the value of the resistance. Does that make sense? Why does it come out to be so? Why does the integrated noise not depend on the resistance? Yeah. So what happens is when you change R, the spectral density changes in proportion to R and the bandwidth changes in inverse proportion to R, and it turns out that the two exactly cancel out each other. Okay. So this is again, it's not a coincidence, it's a sort of fundamental result. As we will see later, to get a certain level of noise, you need to have a certain amount of capacitance in the circuit. Okay. So as you can see, the larger the capacitance, the lower the noise. But the noise is not from the capacitance itself, it is from other dissipative components like resistors. But we'll interpret this more carefully later. Okay. So roughly speaking, we can say that, in fact let me not do this, let me stick to what we derived. Noise of a first order RC low pass filter, the mean square noise is kT by C. Okay. So if C is 10 picofarads, what is the RMS noise or the mean square noise? So kT is this and C is this. This corresponds to an RMS value of 20 microvolts, right? So this again is just to give you a feel for the kind of numbers you will see. So 10 picofarad may be roughly the value of capacitance you will use on a chip. Of course it will be different, but it is not going to be many nanofarads. Okay. So if you plot the spectral density, we wrote the expression for it earlier. Okay. The DC value of the spectral density is 4 kTr, and if I plot SV out versus F, it does something like this. Okay. Where does it reach 2 kTr? Huh? 1 over? Yeah. At the bandwidth of the filter, the spectral density becomes half. Okay. Now what happens if you start with a different resistance, okay, which is lower? It will do something like this. Or if you start with a very low resistance, it will have a very broad bandwidth. It turns out that the integral under all of these curves is the same, and it's equal to kT by C. Okay. So this result has a lot of implications on what the limit on noise in circuits is and so on. We'll do all of that after we completely discuss the noise models for different components. Okay. Any questions on this? How to calculate this and so on? So all we did to calculate this was we replaced the resistor with its noise, and the transfer function from Vn to the output with the input being disabled is first order low pass response, and we integrated this, we multiplied with the spectral density and integrated it to get the output noise. Okay. If you have a first order high pass filter, what is its output noise? What is the output noise of this filter? Huh? What do you think? What will be the spectral density? What will be the integrated output noise? What? So I measure the noise voltage here. What is the output noise? Same. Yeah, it is the same because when I reduce the input voltage to 0, the two circuits are the same, right? I am still measuring the noise voltage across the capacitor, isn't it? Is this clear? So the noise of this is also kT by C. So again, this is somewhat like loop gain. It's not dependent on where you apply the input and where you take the output. If the circuit with the inputs disabled is identical, the noise will be identical as long as you are measuring at the same point. Yeah, one thing is, it of course does depend on where you take the output, but it doesn't depend on what you consider as input. Okay. So the noise of the resistor, which is because of random motion of electrons because of non-zero temperature, is known as thermal noise. So this noise is really thermal noise of the resistor. This is because the origin of the noise is random motion of charges because of some non-zero temperature. Okay. Are these parts okay? So now you know how to calculate the noise in any circuit that has only resistors and maybe capacitors and inductors. So capacitors and inductors don't have noise. We won't discuss why and so on, but somehow the noise is tied to power dissipation. Only dissipative components have noise. Things that only store energy don't seem to have noise. Okay. Now, if you make a real inductor, it will have a series resistance. Because of that, there will be noise. But that noise comes from the series resistance part of it, not the inductive part of the impedance. Okay. Similarly for capacitors. If you make a real capacitor, it can have series conductance and shunt conductance and so on. So those parts will be noisy, but the capacitance itself, the intrinsic capacitance is not noisy. Where are the other places we get noise in circuits? Transistors. So all active elements also turn out to be noisy. Okay. So let's discuss the noise model of a MOSFET. In fact, all of our circuits will be made with resistors, capacitors, inductors and MOSFETs and bipolar transistors if we choose to use BJTs. Okay. So this is the MOSFET. Where do you think the noise appears in the MOSFET? The channel. So is there some region of the MOSFET for which you can give me the noise model? Huh? Resistive region. So in the linear region or with VDS equal to 0, the way we think of MOSFET or what the MOSFET is a voltage controlled resistor, right? So there is a resistance between the source and drain terminals, and we just saw that a resistance has thermal noise. So we can imagine that even this resistance, the channel resistance, will have thermal noise. Okay. Let's say it's biased at a certain VGS. What is the noise current? What is the noise model? Let's say I choose to represent it as a current source. We have already seen that for a resistor we can represent the noise as a parallel current source. So what is the parallel current source value? Here by value I mean the value of the spectral density. If we make an analogy with the resistor, we will use the result from the resistor also. So what is the spectral density of this current source IN? 4 kT? 4 kT GM. What is GM in this region? Okay, let's see. So the current is mu Cox W by L, VGS minus VT times VDS minus VDS square by 2, right? So the answer was that the spectral density of current is 4 kT GM. Does everyone agree with this? If you calculate the GM, that is if you differentiate with respect to VGS, you get mu Cox W by L times VDS, and VDS is 0, right? Should be GDS. So it should be the conductance of this region. Okay. See, it is not GM. GM is 0. When VDS is exactly equal to 0, the GM is 0. Is this clear? What we want is the conductance of this region, basically the conductance of this resistor. Huh? Because it is a voltage controlled resistor and the mechanism of current flow is the same as in a resistor. That's why. It looks like a resistor and acts like a resistor, so we think it's a resistor. What was your objection? Yeah, it could be different, but it turns out to be the same, that's all. So again, we won't discuss the origin of the noise model, but here we are discussing thermal noise, and thermal noise meaning random motion of charges, and the result of that is the same here as in a resistor. Okay. In fact, the way you derive the current equation also is the same as in a resistor. Of course, if the channel is non-uniform, you have to take each part of the resistor and then you integrate over the whole thing to get something more complicated. But the way you derive the current of a MOSFET is by thinking of it as a resistor. Right? So it turns out the noise is also the same. The behavior of noise is also the same. Okay. So it's 4 kT times GDS. So what is GDS here? This is the spectral density of the noise current, and okay. So what's the value of GDS? So this is at VDS equal to 0. Okay. So the fact that the MOS behaves like a resistor, and especially at 0 VDS it looks exactly like a resistor, can be used as an analogy. I mean, this is not a derivation of the noise of the MOSFET clearly. This is more of a derivation by analogy type of thing. But this turns out to be true at VDS equal to 0. This is the noise current of the MOSFET, and it is sort of intuitively satisfying because it is a resistor and its noise should behave like a resistor. Okay. What do you think happens to the noise model as you move away from VDS equal to 0? SID decreases. So what happens in saturation region? Huh? It reaches a minimum value. Is that what you think happens? So, I mean, if you, let's say you, like by analogy or however, you derive this expression and you decide to use this everywhere. Okay. So, what happens to the noise of the MOSFET in saturation region? It becomes very small because GDS becomes very small. Right? So, but this model itself is not right when you go to saturation region. Okay. Because the GDS in saturation region represents something else. It represents the channel length modulation. Right. It has nothing to do with the charge in the channel itself. Okay. So again, we are not going to derive the model and so on. So it turns out that this, again, we take without proof. The noise of the model is, the noise of a MOSFET can be represented by a current source between drain and source. Okay. And the spectral density of this current source is I think it is, 1 second. So this is the noise of a MOSFET where mu is the mobility and Qi is the inversion charge in the channel. Okay. So this is an expression that is valid in all regions of operation of the MOSFET. We just take it for granted without further proof or anything. Okay. What is the value of Qi in the triode region when VDS equals 0? The magnitude of Qi at VDS equal to 0. Cox WL times VGS minus VT. Everyone is familiar with this. A MOSFET when it inverts, when it has an inversion layer, this capacitor has VGS minus VT across it, and the threshold voltage is dropped through between the channel and the bulk. In fact, that's the definition of threshold voltage, right? The threshold voltage is the voltage at which the channel starts forming. Okay. So it's assumed that the voltage across this is exactly VGS minus VT. And it's a capacitor with the channel being the bottom plate and gate being the top plate. The charge in the channel will be the capacitance, which is COXWL times VGS minus VT. So in an NMOS this will be negative and in a PMOS it will be positive. Okay. We just take the magnitude of this anyhow. So if we use this expression, SID turns out to be mu COX W by L VGS minus VT times 4 KT. Okay. This is consistent with our earlier model by analogy. This is nothing but the conductance between, the incremental conductance between the drain and source at VDS equal to 0. So 4 KT times the conductance is the spectral density of the noise current. Okay. So the spectral density of noise current will be always of the form of KT times some conductance, and spectral density of noise voltage will be KT times some resistance. Of course, there will be some constants before. Okay. So here it is 4 KT times the conductance, and it's also intuitively satisfying because at 0 VDS it is a resistor. It is a resistor meaning it's a mechanism of current transport, everything is exactly like in a resistor. So the noise also is like what you see in a resistor. So what happens in saturation region? What is the inversion charge in saturation region? It is not constant. Yeah. So does anyone remember the expression from device physics? What is the total amount of channel charge in the saturation region? What is the value of CGS in saturation region? Huh? 2/3 COXWL. Why do we get this? This is because again the proportionality constant of 2/3 appears in the expression for channel charge. That's why we get the 2/3 form. So the magnitude of inversion charge in saturation is 2/3 COXWL VGS minus VT. Okay. So if I plug this into the expression for the spectral density of noise current, I get 8/3 KT mu COXW by L times VGS minus VT. What is this? What is this quantity? It is the transconductance GM in the saturation region. Okay. So it turns out to be 8/3 times KT times the transconductance in the saturation region. Okay. So the bottom line is the expression, the noise of a MOSFET can be modeled by a current source between the drain and source. Okay. and the spectral density of this current is 4 kT times the mobility times the inversion charge divided by L square. This, if you want to see the derivation of this, you can refer to the book on MOS modeling by CVDs. Okay. I think it's called Modeling and Operation of the MOS Transistor by CVDs. And this SID can be simplified to four kT times GDS at VDS equal to 0, but we will use this in all of triode region. Okay. Even in the triode region, the inversion charge will keep changing. Only at VDS equal to 0 will you have a uniform channel between drain and source. Otherwise, you will have slightly different values, but we will use this nonetheless. Okay. We will use this as the expression for the noise in all of the triode region. And for us, particularly for design of amplifiers, the more relevant region is the saturation region. And in that case, it turns out to be 8/3 times kT times gm. Okay. And this is valid only in the saturation region. So, most of the time we won't use this expression, which holds good everywhere. We will use one of either this or this. But, I mean, you should be careful. If the MOSFET changes the region, the expression has to be changed. Clearly, in triode region, gm is very small, so this will give nearly 0. And in saturation region, GDS is very small, so this will give nearly 0. That does not mean that the noise is 0. It only means that the wrong expression is being used. Okay. Any questions? No. This is valid only for drift conductance. Okay. So, in subthreshold region, we will have a different noise model. We will probably later briefly discuss the noise model in a bipolar transistor, and the noise model in subthreshold region will be similar to that of a bipolar transistor. The important thing to remember here is, for instance, when VDS equals 0, okay, there is no current, there is no DC flowing through the transistor. The current through the transistor is 0, but there is still some noise current. But it turns out that in a bipolar transistor, if the current is 0, the noise is also 0. Okay. Maybe we can discuss it now itself. I think all of you are sufficiently familiar with the basic model of the bipolar transistor, right? So, bipolar transistor, okay. If you plot IC versus VBE, it's the well-known exponential curve. Some saturation current times exponential VB by VT minus 1. And in fact, bipolar transistor follows the exponential law very closely, like much more than the MOS transistor follows the square law. Okay. Frequently when you do hand calculations, this one is neglected. Okay. Now this is assuming that VCE is greater than some saturation value of VCE. Okay. That is basically, you want the base emitter junction to be forward biased, and you don't want the base collector junction to be forward biased. So this model holds good when the base collector current is not forward biased to a significant degree. You can have maybe 0.3 volts of forward bias or 0.2 volts where the current through this junction is insignificant. But if you have significant currents flowing through the base collector junction, then this model is not true. Okay. And if you plot IC versus VCE, it looks somewhat similar to ID versus VDS, but there are some important differences. There is a region where the current is almost constant, okay, and the difference is all these curves merge to almost a single curve, and the zero current is achieved not at VC equal to 0, but at some positive voltage, okay. This is typically what happens. And also very confusingly, this is the saturation region of a bipolar transistor, and this is called the active region, okay. Whereas in the MOSFET, the constant current region is called the saturation region. So a MOSFET has useful applications in the low VDS region, but a bipolar transistor is almost always used in the active region, okay. It's not very useful to use it in the saturation region, in the bipolar saturation region. So this is very quickly the DC model of a bipolar transistor. And the small signal model can be calculated similarly. So again, we will stick to the active region. In the active region, as I mentioned earlier, it is some saturation current, exponential of VB by VT minus 1. And just like the MOSFET, it shows some dependence over VCE. Okay, the current is not exactly constant, but it's only approximately constant. And the proportionality constant for VCE is 1 over VA, where VA is the early voltage. Okay. And also the other important difference is that there is a base current which is related to the collector current by a constant beta, which is preferably very large, okay. But typical values may be in the tens or hundreds at most. So what do we do? How do we generate the model? So we have these two currents. We differentiate it with respect to all of the voltages and get the conductances to get the small signal model, okay. What is this? So to simplify this, I say neglect the dependence on VCE, also neglect the minus 1, that is this minus 1 term, okay. What is this? So it is approximately IC divided by the thermal voltage. Oh, by the way, this I should use a slightly different symbol. This V subscript lowercase t is the thermal voltage, which is kT by Q, okay. And what is this? If you differentiate with respect to VCE, you get 1 over VA from this part of the expression, okay. So it is IC by VA. And what is this? So IB is this. So okay, and you also have another derivative dou IB by dou VCE that's usually neglected in the model. And as I mentioned earlier, we won't spend too much time on this model. We'll just derive these expressions and go with it. Model turns out to be quite similar to that of bipolar transistor. Okay, in fact, it is somewhat simpler because we really have only 3 terminals. We don't have the bulk. We don't have an additional control for the collector current, okay. So just like before, we will have a transconductance that models the dependence of IC on VBE. Okay, this is GM times VBE, and we will have a conductance that models the dependence of IC on VCE. Okay, so the current through this is the incremental VCE times some conductance. It's usually denoted G0. Okay. The additional term we have is an incremental base current as a function of VBE, and this conductance is Gm by beta. Okay. Now traditionally this is denoted by a resistance R pi, and R pi is nothing but beta divided by Gm. Okay. So this is the model of a bipolar transistor. This is the model we will use. So if you read like older textbooks on bipolar transistors, you will have the model with RE or lowercase re, which is basically the reciprocal of Gm. Okay. We won't use that. We'll use a model that is similar to the MOS transistor model, so that our analysis carries over between the MOS and bipolar circuits. Okay. And this model also we find is more convenient to use than the other model. Now the model of MOS transistor in subthreshold is the same as this, except that this part, this conductance is 0. Okay. So if you have a MOS in subthreshold, we will have only these two elements. Okay. And we won't have this one. Why does the noise appear in a bipolar transistor? In a MOS transistor, it looked like a resistor, so we said because of random thermal motion, we have noise. Why does noise happen in a bipolar transistor? Huh? Junctions are? No, it's not exactly that. Okay, So actually, the bipolar noise model is also somewhat complicated. The model is not complicated. The analysis to get the model is complicated, and I don't understand it very well. But what I will explain is roughly how the noise happens in a bipolar transistor. It is somewhat similar to the vacuum tube, if any one of you have seen or heard of a vacuum tube. So what happens is, if you have in a vacuum tube, you have a hot plate which emits electrons, and this is biased at some negative voltage, and this is, let's say you have another plate biased at a positive voltage. So electrons fly from one side to another to give you a current. Okay. Now the average rate of flow of electrons is the total current, which, I mean, if the electrons are flowing this way, the current is this way, and let me call the average current IC, just for the heck of it. Now what happens is, if you sort of take a cross section of it and time the electrons, it's not like a uniform stream of charges that is flowing across this. Okay. The electrons are discrete, and also the time interval between successive electrons crossing the barrier is not a constant. Okay. So if you plot the current that is flowing as a function of time, now first of all it flows in discrete packets. So what will be the form of current? If I plot I of t versus t, what will be the current? Maybe, sorry, let me not even plot I, let me plot like q. What will be q versus time? What's that? Yeah, it will be some discrete points. Okay. So if you plot the accumulated value of the charge as it goes from one side to the other side, it will be maybe one electron appears here and the next one appears here, next one appears here. The heights are all the same, of course. And something like this. Okay. And if you plot the current, what do you get? It's the derivative of this, right? What is it? It's a set of impulses. So, okay. And the area of each impulse is the charge of the electron. Okay. So, the meaning of noise here is, first of all, the I is not constant, right? It is a set of impulses. And the average value of I is some particular value, IC. Okay? So, the difference between the actual current, the impulsive current that flows and the average value, that is the noise. And it turns out that the arrival times between these are in a Poisson distribution. Okay? So, Poisson distribution, you know what it is. It's the inter-arrival times are exponentially decaying. So, you see a lot of instances with a short inter-arrival time, but fewer instances with longer inter-arrival time. So, you see some bunches and then some spread out area and then some bunches and so on. So, that's the, if you see a Poisson process on a, plotted on paper, that's what it looks like. You see a bunch of impulses and then nothing, or sparser bunch, then a denser bunch and so on. So, there is some bunching, that is what you see. So, this is the noise, and it turns out that if you evaluate the spectral density of this from the Poisson distribution, it turns out to be 2 times the unit charge times the average current. Okay. So, if the unit charge is Q, so let us say you had a process where you had a certain unit charge Q and the unit charges were appearing at random intervals and the random intervals were distributed according to the Poisson distribution. Then the difference between the instantaneous current and the average current will have a spectral density of 2Q times IC. Okay. So, the key here is if you didn't have an average current, if the current was 0, then the noise would be 0 because there is nothing, right. Okay. So, this is true for a vacuum tube where you really have literally some hot plate and electrons flying off that from one plate to another plate. Here is very easy to imagine a scene like this, right. The charge is coming in discrete packets. On average, it gives you some current, but instantaneously it is not that constant current. Okay. The difference between the two again turns out to have this distribution. We are not going to derive it. Now, yeah. What's that? Why? No, actually it turns out to be white also. Okay. In fact, there is some time constant associated with the Poisson distribution. Okay. So, it turns out to be 2QIC, and then at this time, at the reciprocal of this time constant, it goes to 0. Of course, this time constant is very large. So, for our purposes, we assume that it is white. Okay. So, this is the spectral density. Now, in a bipolar transistor, the scenario is even more complicated than this, but the model turns out to be exactly this one. Okay. This is the noise spectral density of collector current in the active region. It is 2Q times IC. Okay. So this is not thermal noise. This kind of noise is known as short noise. The term comes from, again, the analogy from the vacuum tube era, where electrons firing looks like shots being fired. Okay. So we'll continue this tomorrow, but the noise in the subthreshold region of a MOS transistor turns out to be similar to this. Okay. It is 2Q times the average current flowing through the drain. Okay.